see. Okay. To the kind of water softening stuff, I am having internet trouble, so there's a thing or two that I wanted to do, not going to be able to do, and of course the live stream is not operable, but I'll record this for your reference. Okay, so I think I left off talking about hardness, kind of just briefly mentioning it. This is one of those aesthetic water quality parameters that is not necessarily mandatory to change it or to adjust it for drinking water treatment and distribution. This is the hardness here. It's not actually like physically hard as we think of hard, but it's a term we use for mineral content, essentially. So specifically, and we won't really get into it too much, but calcium 2 plus and magnesium 2 plus are the major ones, and then anything else with what we call a multivalent, so more than one positive charge. They tend to have a few effects on our water, including precipitation. If you let water spill on the sink and then it evaporates, and that happens repeatedly around the sink, you'll get mineral scaling, mineral deposits. It can be important for like hot water heaters, things like that. So industrial as well as municipal issues there potentially. And then it also affects our soap. So it turns out soap molecules are generally kind of squiggly things, and a lot of times they'll have positive sides and negative sides, or different characteristics in some places where it's less polar, maybe in the middle or something. And what happens if you have the 2 plus charge is, instead of being perhaps like a long and flexible thing, it'll transition into, if you have a 2 plus ion of some sort, it'll kind of grab a lot of that soap molecule and it'll kind of fold around it. That's maybe a good way to think about it. So you end up needing more soap if you've got all these ions, because you have to kind of satisfy them, and then the extra soap can do the lathering like you'd expect. And this will change just simply based on the natural geology. So how much mineral content is there in your groundwater source, or in your river water flowing through, what kind of rocks are not native to that area. That's all going to determine how hard your water is. So for example, I grew up northern Georgia, kind of that area, so you can see on the scale that's pretty soft water. We measure it as milligrams per liter of calcium carbonate. It's the calcium in there that's really kind of what we're talking about there. You don't really need to know too much about that. I'm just kind of describing what's here. So we've got 0 to 60 is pretty soft, whereas the very hard is 180 to 250 milligrams per liter calcium carbonate. I then spent a couple years in Michigan, so right in this little area, and you can see maybe I had hard or very hard water, somewhere around there. And now that I live here, it's somewhere, don't know exactly how well this is drawn or how well I can pinpoint it, but it looks like pretty soft probably, or if we were to go down more towards New Orleans, or if maybe we're in that little spike there, maybe it's fairly hard, but not excessively so. So if you've ever lived somewhere else or traveled somewhere else and noticed the water just acts differently, maybe when you're washing your hands or like in the shower or something, if it's really soft, it'll actually feel like you can never get the soap off. It'll kind of have almost like there's a slime layer left, even though you can see it's clean, feels clean when you dry it, but like that layer of water, there's some aspect there and we'll talk about it as we get there, but there's kind of a layer preventing contact. We're going to manipulate that layer when we cause particles to stick together. So we'll come back to that concept. But hardness in general, it's just kind of interesting. Not a major thing, but if you do get a chance to travel and you think about it, see how the soap is acting, and see if you can see mineral deposits. If you can never get soap bubbles, you can never get the lather effect, then look around and you'll probably find some mineralization along the sinks or something. Okay, so with that, wanted to give you a big picture of a typical drinking water treatment plant and kind of identify where we're going to start and we'll walk through the different steps here. So first of all, if we're pulling in water from, let's say, the Mississippi, there's a whole lot of stuff there, and we're just not sure what we're going to get, right? So the first thing we would do is use some sort of a barred screen rack, probably at our intake, and potentially an additional one right at the spot where the water line meets the treatment plant as well. In addition to just a simple screen to catch any logs or basketballs or whatever happens to be floating in there, fish, all that. In addition to that, we would want a grit chamber, which essentially collects all the sand grains, the heavy particles that could really mess up our plumbing and our pumps in the system. So we want to catch those. It doesn't require a lot of effort, just sort of a mesh screen type of thing, or a pretty rapid sedimentation sort of a system to catch all that. Then we go into what we call our primary sedimentation. And by the way, these are, so far, we would see both of these in a wastewater treatment plant as well, right? Especially if a wastewater treatment plant had some storm sewer type connections, which we try not to do anymore, but you just never know what's going to end up in your sewer system, especially when you have the storm sewer connection. So if that's the case, you want to screen it out, catch the small stuff, anything that could harm your plumbing. Then we use gravity. And that's what we're talking about today, is how do we use gravity? How do we design a system? How do we know something about the particles themselves in order to apply sedimentation with some precision or I guess, accuracy? So that we'll use sedimentation here, get what we can to fall out of solution. Then we will add in some chemicals to cause particles to stick together. Larger particles will fall faster. And so then after that, we'll do sedimentation a second time and collect all the sludge and junk, process that, probably dewater it, send the water to wastewater, and just landfill the solids. And then move on with our different treatment steps. So sedimentation is what we're talking about today. And it's kind of obvious, right? We want to use gravity. Gravity is abundant, free, and available. The only thing is we're just going to need to give it some time. So to consider how to use gravity, we need to first consider a force balance on a particle. And so we're going to make some assumptions so that we can handle some particular types of particles. And it's not going to be necessarily all particles, but we can make an assumption to say, hey, if we can remove this type of particle, then sure enough, we should be able to remove, many particles like it. And so that can be our design criteria, is assuming a spherical particle. So we'll say assume spherical. Going to make our math a lot easier and really possible. And I'll say identical. We could get into some more empirical, like trial and error type tests to see, okay, how well are these things sedimenting? There are techniques and stuff like that. We might mention them later. But for now, we're just going to do a simple case, discrete particles. So we'll say assume spherical, identical, and discrete. So until we cause them to stick together by our coagulation, we're assuming they're individual particles hanging out in solution. Okay, so to think about it then, maybe this particle on the left's reality, and we assume it's then the one on the right. And the force balance we're going to have is going to be gravity, obviously, pulling down. So force, gravity. That'll be opposed by a buoyant force. So if you try to dunk a beach ball in a bathtub or swimming pool, you'll have an effect where it's pushing back, right? The buoyant force. That's based on the amount of mass displaced by the object. And then assuming we get some sort of a velocity one way or the other, then we get a drag force. So if we assume that we are having a particle moving downward to settle, then we'll have a force of drag to compete with. And that's going to depend something on the viscosity of the water, the area, the cross-sectional area taken up by the sphere, and all that. Okay, so the object of all of this is going to be to find a terminal velocity, the speed at which the particles are falling. So we'll say a terminal settling velocity, Vs. That's what we want in order to know, okay, how big of a reactor do we need to design to give it enough time for it to fall to the bottom before the water moves away, essentially. So we'll elaborate on that aspect in a minute. But first, let's take a look at the force balance and even our force equations. We'll derive a nice equation accordingly, and we can use that for our problems. So here we have force of gravity as mass times acceleration. So the mass of the particle. I have all of these terms written out more elaborately on the next slide, so I'm just going to talk it through, and then you'll have all the information posted. So mass of the particle times the gravity. For the buoyant force, we have mass of the water displaced times the acceleration due to gravity. And then this drag force is a function of the viscosity of the surface area that's moving through. So we have pi in there. The diameter of the particle. Turns out 3 mu pi times that velocity times the diameter. Not going to worry about that specific derivation or any of that. I'm just taking that for granted. That's what it is. Now, for the gravity and the buoyant force, it turns out it's really hard to select one little particle out of the water, and we're talking like less than millimeter-sized particles. Like we'll do an example problem later that's 1/100th of a millimeter, right? So 10 micrometers sized particle. So it's really hard to pick that up out of the water, dry it, put it on a scale and weigh it, and know something accurate about it. Right? That's not really happening. So instead of mass, what we can do is get some estimation of the volume and some estimation of the particle density. And that's something we can do a little more easily if we get a bulk, maybe a filtration or something, get a lot of these particles and analyze them that way. We can also use, instead of volume, we could use diameter, can give us volume, assuming it's spherical, and we can get that with a light scattering technique that's pretty simple. It's rather quick, and so we can get pretty good information, or at least workable information, in the form of volume and particle density. The added advantage here is if we already go through the trouble to figure out the volume of these particles, then we now know the volume of mass of water displaced, and combine that with the density of water. Then we can get a term for mass with values that we can actually use in our system. And one thing to note here is our density of water and our viscosity are both temperature dependent. So it turns out that sedimentation operations in the middle of winter are a bit different than in the middle of summer. Water's a little more viscous when it's colder, and slightly less dense when it's hotter, for example. Okay, so all these written out here. The mu is dynamic viscosity of water. The units here, all of these units are written out as we need to use them. Of course, sometimes you will not be given a particle size diameter in meters. You'll need to convert it to meters, right? So you'll be given, let's say, millimeters or micrometers or something like that, and you'll need to convert back. Okay, so we've got dynamic viscosity of water, the settling velocity, meters per second. So typically, if we're talking about a particle settling slowly, that's not very many meters in a second, right? It's actually going to be a small fraction. So typically, for most of our systems, this is probably going to be something like 10 to the minus 4 or 10 to the minus 5 as kind of reasonable numbers, just based on my memory. So definitely a small number for meters per second. If it's falling that fast, like as if I were to drop this in air, then clearly we didn't really need to design a sedimentation tank. It's just gonna come out before it even reaches our pipes, really. Okay, so then we have diameter of the particle. A lot of times this will be something like 10 to the minus 5th meters. So 1 to 10, maybe 100 micrometers. We've got the acceleration due to gravity, which of course is 9.81 meters per second squared, or 9.8. We have the mass of either a particle or the water. That'll be in kilograms, because again, we have kilogram units all throughout. We've got volume of the particle, and here we're using cubic meters, because if we do the diameter of the particle in meters, then we need the volume in cubic meters. So we're really going to have a very small number if we ever deal directly with the volume, but it turns out most of the time we'll just be in diameter anyway. So then we have the density of the particles, so rho p, again, kilograms per cubic meter. So kind of a bulk scale value here. Sometimes you'll be given in maybe grams per centimeter cubed or something, and you'll have to convert. Our density of water is also in kilograms per cubic meter. That's temperature dependent. And if you remember, we said at 5 degrees Celsius, we've got 1 kilogram per liter. So that means if we do the conversion, that's 1,000 kilograms per cubic meter. There's 1,000 liters in every cubic meter. Okay, so, and just as, that's a good reference point to kind of think about, the 1,000 mark is typically close to what your water value is. And as you'll see in a few minutes, the difference between the density of water and the density of the particles, that's going to be the driving force for the buoyancy, right? So the bigger the difference, the faster you're going to go, in some sense. That'll be in the relationship we'll derive in a minute. Okay, all that makes sense so far, terminology? Yeah. So let's do the force balance. Essentially, as I mentioned, our goal is to find the terminal velocity. So we want an equation for Vs, as we see down here. And so we're going to derive it starting with, we'll use the right side of these two. And so we'll go ahead and set it up. Of course, the force of gravity is going to be equal to the sum, once we reach terminal velocity, like skydiving, right? You reach a terminal velocity once the force of drag is opposing you with the same force as the force of gravity is pulling you down. So you reach 80 plus miles an hour, whatever it is, 180, I don't know. You reach some speed, and then the force of drag on your body for the skydiving situation, that's what's opposing you, that's what's slowing you down. There's not really enough buoyancy force to care about, even though you are displacing a little bit of air. It's negligible. But in water, we're going to have the buoyancy force plus the drag force, and the drag force is correlated to how fast you're moving through the water. And that's why we have the velocity term in the force of drag equation. And that gives us a way to find it, because at some point you're going to be slowed down by the drag. So that's how we reach an equalization. That's what gives us f of g equals, that's what gives us this here, right? At some point, those two forces, the buoyancy and the drag, are going to equal the force of gravity. So we start there, and we say the volume of the particle times the density of the particle, rho, times g, equals volume of the particle times the density of the water it's displacing, times g, plus this 3 mu pi Vs dp. Okay, so I'm going to go ahead and get the terms, the Vs term by itself. So I'm going to move that over to one side, and we'll have Vs. I'll leave it in this part for now, 3 mu pi dp equals V particle times density of the water times gravity minus, excuse me, I did that. This needs to be the density of the particle. Subtracting this side, this guy from both sides. This will be minus Vp density of the water times gravity. Okay, so from here we can do a couple simplifications to it. I'm going to go ahead and extract out of these two terms the VP and the G, and then I'll divide everything on the other side, so I'm just going to continue here. So the VS, and I'm going to try to make this a kind of a little bit curly to show this is a lowercase v. That's our velocity, not to be confused with our volumes over there. So our velocity, terminal settling velocity, is equal to then volume of the particle times acceleration due to gravity times rho of the particle minus rho of the water. So like I said a minute ago, and I'm not done yet, I have to divide. Like I said a minute ago, that difference between the densities of water and the particles, that's a key driving force, right? And so we see that here, the density of the particle, if it is larger than the density of water, our value here is positive, and we have that difference is driving this upward, right? This is causing more velocity. Okay, so this is all divided by that 3 mu pi dp. Okay, so that's fairly useful, but we can actually simplify further if we recognize that we made that assumption about the volume of a sphere, right? That we have spherical particles, and we have this volume term. We can just put that into diameter terms and not even worry about volumes at all. So that's going to be convenient once we remember the equations for a sphere in terms of the volume, right? So the volume of a sphere is what, 4/3 pi r cubed, right? And so we want to change that r to diameter instead of radius. And so let's say Vs equals 4/3 pi diameter over 2 is the same thing as radius, cube that whole thing. And so that becomes Vs equals 4 over 3 times 8, 4 over 24 pi diameter cubed. I'll go ahead and just write the particle there. So, sorry, I put S for sphere, and that was a very bad idea. I'm just going to say volume there. So the volume of a particle then is, we can write as that, or we can say that's 1/6 pi dp cubed. Okay. Does that make sense? All right. Good. Okay, so then the last simplification, then we will essentially insert that term instead of volume here. So we'll say our settling velocity is equal to, and I'm just going to go ahead and write it 1/6. I'm going to go ahead and write this volume term here. It's just multiplying across the whole thing. So 1/6 pi dp cubed. And then I'm going to continue writing the other stuff. We have a acceleration due to gravity, rho p minus rho, divided by the 3 times mu times pi times dp. Okay, so we've got all of that. Simplify the last bit, and we say Vs then is equal to, the pi's will cancel. On the bottom, we'll be left with 18 mu, because the dp will also cancel with one of them up top. So we'll end up with, and I'll just write it out exactly how our book has it, with gravity times that difference in density times diameter of the particles squared. Does that make sense? Good. I'm giving you this equation on the exams, but the point, in large part of the point of going through this with you here is so that you kind of have a better understanding, I hope, of what's going into the sedimentation velocity. Because if you think about, well, what happens if we change the particle size versus what happens if we change the gravity? Let's say we try to do it on the moon, right? What happens? Or what happens if the water becomes more viscous? What happens if you try to do this in honey? What about ethanol? It just happens to be less viscous than water, right? You can start thinking about, oh, if I change one of these parameters, it's going to affect my velocity because here it is in the turb. And if you see here, you might think to yourself that the density would be like the major controlling factor, but it turns out that the diameter is perhaps more important because it's squared, right? So the density is important, but if you double the density, you're getting a doubling of your impact. If you double your diameter, you get a quadrupling of your velocity, essentially. Okay, so how do we put that in practice? Well, there's a couple of reactor styles that are used most commonly that we'll talk about. Those would be kind of these circular ones you see on the left, and then just rectangular, kind of like a big swimming pool type of things on the right. And it turns out both work very similarly in that you have water flowing across and particles sedimenting down during the time. And you could even take one of these circular ones, which are essentially they're pouring water out from the middle, and it's heading out to the sides of their chambers. It's collected on, it's sort of a radial system, and it's collected around the edges. And so if we take a cross section as if we went down into the swimming pool, so to speak, and looked in from the side, we could draw it in this way where we have flow going through, we have height this direction, we have a length term here, and then we could imagine the width out that way. This would be the rectangular one, but it turns out we can also draw a cross section at some radius in the circular system, and that would give us a similar rectangle if I could draw properly. We could get a rectangular there too, just based on the flow from the midpoint to the edge, right? It's just radial flow, and then instead of the width here, maybe in that case we would say our area on the bottom will be curved, and we have a circle to deal with. But in either case, we can see that we have a height, we have a length that the particles are going to travel, the water's flowing that way, and then we have some ability to measure the surface area at the very bottom, which will come into play in a minute. Essentially what we want is, as particles are flowing through, we want them to be falling to the floor. As soon as they hit the floor, we count them as separated. They're going to stick to other particles, they're going to stick to the ground. They're no longer suspended in motion in the water column. So that's really our design criteria is how can we get the particle that starts at the very top of the water to meet the bottom before escaping. Okay, so that's going to be, we'll hit that, elaborate on that here. But so ultimately that's our design criteria, is we want all particles removed of a particular type. We could go crazy with this and say we want to sediment viruses until we realize that viruses are so small that just the Brownian motion with diffusion is going to keep them suspended. They'll never sediment. They're not small enough to sediment, or they're not large enough to sediment. So sometimes, at some point it becomes completely impractical. And those are typical viruses like 30 to 50 nanometers in size. So that would be 0.03 to 0.05 micrometers. So usually we're talking about at least a micrometer, probably tens of micrometers in size as a kind of a limit to the particles we can sediment. Okay, that said, let's take a cross section again, and we're kind of considering a system here where we have the height of of the system. We'll have flow going through that way. So this would be our length, and we can imagine that we have some width to this reactor as well. So this is not the top down, this is a side view again. And we're going to look at a lot of these in kind of the side view sort of case. So the height of a given particle, let's say in a given particle that we want it to reach the bottom right at that edge, right at the corner. That's like the minimum speed it can go in order to reach the bottom. Any slower downwards, any slower settling velocity, and it's not going to make it, right? It's going to escape. So that's what we don't want, is we don't want it escaping, and so we're going to design our system in order to prevent that. So the height of a given particle, I'll just say this particle is HP. If that's our design criteria, we want the height of the reactor to be set equal to the height of the particle so that we can convert from the actual settling velocity that we observe or calculate to the critical settling velocity that's going to be our reactor design. So we'll try to elaborate here and make that clear. So if we think about the downward component of this slope, and that is going to be like this, the horizontal has something to do with our flow, right? That's the flow speed. The downward component for this particular line is what we call V naught. That's our critical, our design settling velocity. For a given particle, no matter where it is, that would be Vs. I'll call that one Vs1. Or we could have a particle that's going really slowly. That would be Vs2. For example, the downward component for each of those is what I'm talking about, causing them to fall at some speed in relation to how quickly they're going through. I'm going to erase those to just keep the picture a little clearer, but this is what I'm talking about. You can Vs is some random particle, and V naught is the particle speed that's required in order for it to just barely be removed. Okay, so I'm just trying to distinguish those two. I'm going to write it out a little bit as well. So Vs we'll say that's the settling velocity of some random particle. I'll say some chosen particle. So probably arbitrary. It's like, oh, let's select this one and see how quickly it goes. Or, oh, let's imagine a case where it's a little bit larger. How quickly does that go? This is my Vs, right? So Vs, when we design a reactor, sometimes we select a particular particle we want to remove, and so we compare Vs to V naught, this critical velocity, but they are independent. Okay, so then for design, I'm just going to go ahead and write this V naught is reactor design. Just think about reactor design when you're thinking about Vs. Okay, so in order to design a reactor this way, to say that we want, for a moment, to set V naught equal to Vs in order to remove a particle at the top of the column, that means if that one's removed, everything else is going to be removed, right? So if this particle here gets removed, anything that's falling at the same speed lower than that, if I draw that parallel, is also going to be removed. Okay, so that's why it's critical. That's kind of the key point. We'll say that we'll do that when H is equal to HP. And so then we can say, well, how long does a particle have in the system? The water's flowing through, There's some amount of time that it has to be able to reach the bottom. That's our design criteria. So we're going to say, from simple physics, that the distance traveled downward is going to be the speed at which it's traveling times the amount of time it has to take, right? And so here, since we're saying H is equal to HP, to design the reactor, we're going to say H is equal to that Vs. And now we can write it as V naught, because we're doing the reactor design, times theta. Okay?
So in this instance, theta is time?
Theta is time because remember that theta is hydraulic retention time. So theta is the term that our book uses for hydraulic detention time. And thank you, that's a great clarification. And we have an equation for that relates to our reactor size and the flow rates we need, and that is theta is V over Q. So we'll rewrite this as H equals V naught times the volume of the reactor over the flow rate. Okay. So it turns out we have a way to know something about, to simplify this further, because we know our volume relates to the height of the reactor. So since we are designing this as based on the height of the reactor, that's kind of our design scheme here, we're going to say this is equal to V naught times, in this case, length times width times height is going to be our volume for a rectangular system, right? So it's going to be V naught times, really, the better way to say it, instead of doing length times width times height, it's going to say the area of the basin, AB times height. And that divided by our flow rate. And I'll just say AB is area of basin. That way it can be length times width, or pi r squared, in the case that we're doing a circular system, right? So whichever area is appropriate, we'll use that one. Does that make sense? Okay. All right. So with that, we can take this and simplify, because we just said H equals V naught times AB H over Q. Let's find an equation for V naught, and we can divide both sides by the area times height and multiply both sides by Q, and we get V naught equals the H's cancel, and we end up with V naught equals Q over AB. And we can stop a moment and think about this and say, okay, V naught should be some settling velocity, right? That's the critical settling velocity, so it should be in meters per second. So we can double check that we did the math right by making sure that the flow rate, which is cubic meters per second, divided by the area, which is meters cubed, or meters squared, that does give us meters per second. So good. So that then is a simple equation that gives us the design criteria for a sedimentation basin. What's interesting here is you'll notice that the height went away. You think about, a chamber that's supposed to let a particle settle some distance. You think to yourself, well, the depth is going to matter a lot because it has to settle some depth. But it ends up that information is captured within the flow rate and the area. So if you think about pouring a bunch of water, let's say through a narrow pipe, it has to go pretty fast compared to if you have a wide pipe, right? And then if you think about, well, what happens if you let the height in there vary, you could have, based on a change in flow rate, it's going to change the height, essentially. Or you can kind of think about it in that manner. And the height ends up not mattering in our equations because it's taken care of there. All right, any questions? Okay. So what happens when we have a situation where Vs is not equal to V naught? So if this is our particle that's traveling downwards with V naught speed, then what happens if we have a particle traveling slower? Right, we'll call this Vs1. We could also think of a particle, earlier I said it travels faster, it's going to be removed no problem. We could also think about this same particle traveling at Vs1 that happens to start lower might actually be removed. So if that's Vs1, or let's assume it's parallel, I don't think it quite is, but if that's also Vs1, that one's removed, but not all of them are, right? So how do we deal with that is kind of an interesting question. And one thing you notice here is if we compare the Vs that we measure, or for some random Joe particle, that particular particle, we can compare it, is it greater than or less than V naught, will tell us some information about the settling, right? So if the V naught is faster, so if, well, it's written here, right? So if the V naught is faster than the particle, not everything's going to settle. Or you could rewrite that if Vs is smaller than V naught. It's just a difference in speed, right? If it's going down slower than what we designed for, it's not necessarily going to be removed. We will notice, though, there's probably some portion of them that will be removed. So if we were to draw here the distance between there, that should correlate kind of in an interesting way with the same velocity line. If we draw it from here up, we should end up having some geometry to work with. We'll get to that in a second. Okay, so we might get some particle removal, but certainly not all under, if we're missing the mark. All right, so just wanted to draw that up a little bit more clearly. Let's say just one speed where we don't have, we'll just say the settling velocity is less than V naught. So we have a system like that. Stop. Okay, if we have something like that, then we can compare just like this to say, well, some portion of them are removed, and that portion is graphically shown here, just based on that. So we could label these, right? This could be section A, and this is section B. Well, that's going to be B and A over here, just based on basic geometry. So that's pretty convenient, and then we know, okay, well, some portion B is removed, and that leaves some portion A that never got a chance. They all escaped. So that actually gives us a way to directly relate the settling velocities to the fraction of particles settled in such a system. So, and I meant to include a slide here about that, so I'll just write it up instead. So if we say P is the particle removal, percent of particle removal, percentage, we can define the P as the ratio of Vs to V naught times 100%. And we can do that on the one hand because nothing in the system changes except how fast it's going down, and that means how fast it's going down correlates directly to the distance that it went down or didn't, which will become that proportion. So because of that, we see P then is Vs divided by V naught times 100%. And just to make a kind of obvious point, we'll say P cannot be greater than 100%. Right? So Vs can be greater than V naught, obviously. We can have particles that settle very fast, but that doesn't mean we settle more than 100% of those particles, right? So it's kind of all or nothing, or really it's either all or partial, okay? So it's 100%, or maybe if we don't remove all, then we have some partial amount. Okay, so basically those are the two key design equations we have for our sedimentation systems. One is this P. So I guess we have three, right? We have the P, we have the Q over AB for V naught, and then we have an equation to find the settling velocity based on the force balance. Okay, does that make sense? All right, so this is actually not going to make use of all the mass balance or the chemistry we just talked about recently, but those both will come into play once we start adding the coagulant. Okay, so here's an example problem. I was going to do this as a Kahoot assignment, and if the internet starts working in the next 10, 15 minutes, maybe we will. But go ahead and take a few minutes to work this problem. I'll probably, so I will read it through with you. I'm happy to talk you through a couple steps here and there. It'll be a good challenge to put this information to use. It's your first time really seeing it, so I'm not expecting everybody to get it all the way. But again, I think it's nice to have that challenge to push you to apply what you've been learning or thinking about. It's a problem from our book. It says, silt removal in a clarifier. A drinking water treatment plant uses a circular sedimentation basin. Always a good idea to go ahead and draw your system. So we've got a circular sedimentation system. That would imply that it's going to be like a cylinder. To treat 3 million gallons per day of river water, it gives that acronym and a conversion for you there. Then it says, after storms occur upstream, the river often carries 0.01 millimeter silt particles with an average density of 2.2 grams per centimeter cubed, and the silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep and 21 meters in diameter. The water is 15 degrees Celsius. So, got our values here. And just a friendly reminder to also look at the units for the values, if I can find my cursor. Okay, so A is what is the hydraulic retention time of the clarifier. That's our theta that we mentioned. So theta, that's V over Q, you should remember. And B, will the clarifier remove all the silt particles from the river water? So that one is essentially asking, is Vs greater than or equal to V naught? If so, our answer should be yes, right? Okay, so I've helped you out a little bit. There's definitely a lot of units to convert. Good chance to make sure you're familiar and comfortable with those and don't miss them. So I'm going to let you work on that for maybe 15 minutes. You guys are welcome to work together. I'd like for each of you to derive your own answer, though.
We're looking at a circle, so it's just area of a circle times height. But I think that might have to going down the right path.
Yeah.
So I converted everything over, and then we just go straight for ES. I don't know why I saw the area. It's in another area. That's why I got load straight. But then this is volume over Q. So this is what I'm putting in. Yeah. Okay. Volume would be this then. Volume of the cylinder.
How you want part A, part that?
Volume tension.
If you're getting set up velocity, you're already over 50 degrees.
Well, I did. Some of it was gravel.
So you have the flow rate,
Yeah, that was good.
you have the volume of the reactor.
Yes.
Also given, but not.
Yeah.
Theta becomes pretty straightforward.
So theta's literally just okay.
Yeah, part A is a warm up.
Understood.
I mean, I think
I'm
all
with
of those
the
things
wrong
will be useful, but
Yeah. So, thank you.
I did get internet, so we will do a Kahoot in about 5 minutes or so, maybe 10 minutes if you guys need. So keep working to get your own answer. I'll have you answer for that. I mean, welcome to work together just to get your own answer.
Volume is the area times the area.
How are you doing? Do you need a few more minutes or good? Close enough? All right. So go ahead and log in here with your 89 number as your your name. We'll see how you did. Well, we don't have time to go through the solutions today, but we'll do that as we start next time. Don't use dashes, please. It'll be my plan is to import it directly into Excel. So if you put in a dash, if you can see if you can back out and remove it again, that'd be great. Thank you. All right. Anybody need another minute to get in? Just wave at me if you do. Okay. All right. So, what'd you get for problem A? Or which one's closest? If your phone kicks you out, the game pin is at the bottom right still.
When you gave us the second answer, I was like, oh,
All right. So it looks like most of you got that. That's good. Again, we'll come back and I'll explain that later. And by the way, even if you do get something wrong on these quizzes, I reserve the right to grade them, but in grading them, you'll get most credit regardless, or I might just take them as full credit because you're participating. So be warned, I might count it against you, but not by much. So it should be enough incentive to motivate you to try, which I think will inspire more learning. Okay, so what did you get for part B? The question is, will it remove all particles or not? Got 50-50, if you weren't sure. All right, so the correct answer was no, and most of you got that. That's good. Perhaps good guess for some if you didn't quite get there, but again, we'll get that answer next time. Okay, last, do you think sedimentation would be a viable treatment strategy on the space station? Okay, good. Most of you said no. All right. That's about it for today, although I will say I'm going to try to get you your first homework posted today or tomorrow. So be looking for that. I'll post it to Moodle. And we'll see you guys on Thursday.